Right, well, we'll start off with understanding units of electricity, what we're talking about when we're talking about volts, amps, and watts, and how they relate to something called resistance and ohms. Anyway, volts. Let's start off with volts. Here's a table from Wikipedia showing a load of different voltages we're talking about. Now, as you can see on the left, it's a measure of, almost imagine it's like the pressure of a water system. It's how much force is, it's called electromotive force quite often, it's driving the electrons down through the wires. Now, that's probably, in layman's terms, the simplest way of doing it. If you study physics, it's a very, very complicated phenomenon, what you're talking about. But just think of it like the pressure of a system. You can see here, when we're talking with electronics, we're really not using very much pressure at all, not very much voltage here. These are the kind of signal voltages that we deal with when communicating, making decisions and computing. And then if you want to drive something physical, like lighting or motor or heating, you'll probably need more volts. Now, you'll notice here we've got two things here, an electric chair and an electric fence. Now, actually, the electric fence is even higher voltage than the lethal electric chair. So what's going on here? How come this doesn't kill you, but this does? Well, the difference is what's called current in amps, and that's how much flow is allowed to go. So you put a pressure on the system, and if you give it a nice big wide almost channel like a motorway to go down, a lot of current's going to go through there, and that's what makes things hot. So current measured in amps, and it's often referred to as I in symbols or in formula, it's very much the energy that is going down through the wire. So give yourself a nice big fat wire, or in this case a spanner, and a lot of current can go through. So if you combine the voltage and the current together, you get the total expenditure of energy in a system, an electrical system. That's often called power. Sometimes it's called wattage. It's not actually the correct term. It's power, basically, which is measured in watts. So here you can see we've got a triangle. Power is amps times volts. Power on the top means the other two get times together. So if you're wanting to work out the current, it's power divided by volts. Common use of these triangles in physics and whatnot. Here you can see this serial plate of a compressor. It's an industrial one because it's 400 volts as opposed to 240 volts, and the motor's consuming 900 watts. So you can do that simple formula: 900 divided by 400 volts, 2.25 amps. Now this little battery, it says it will deliver 2.2 amps or 2,200 milliamps for 1 hour. Or put it another way, you could consume 4.4 amps for half an hour. It's just a way of describing the battery capacity. Incidentally, this is the theoretical maximum, but generally you wouldn't want to specify a battery to consume absolutely all of it, especially a lithium ion. They don't tend to like being drained completely, so this is an absolute total capacity. Generally you wouldn't want to kind of go for that amount, but anyway, you can see here, if you times the two together, you can see that this battery would power something 2.64 watts for an hour theoretically. So timesing the two together gives its power. So yeah, going back to this is what I was going to say before. I mentioned the big wide cables here allowing a lot of electrons to flow down through that wire, creating a lot of current. That's determined by the resistance. So that is things in the way, and particularly we do actually use little tiny components that will limit the amount of flow of current through the wires. They're called resistance. So think of them like kinks in a hose. They're just going to limit the amount of flow. Now, the relation there is Ohm's law. Now, the volts is the amps times the resistance, if you see that symbol there. If you need to remember which way round it goes, I always think of the point of the V reflecting the point of the triangle there. So you can see that kind of visual analogy there. That's my way of remembering it anyway.
I'm going to do a little practical experiment here. I've got 3 AA rechargeable batteries and they're all rated at 1.2 volts when fully charged. Now, they're connected, even though it looks like they're connected in parallel with each other, they're actually connected in a line like this, in series it's called. Now what happens there is the voltage, if I look at there, is added up. So here, instead of 1.2, I've got 3.843. Let's call it 3.8 volts. So they're well charged up. They're actually slightly higher than their rated amount. And being connected in a line in series from plus to minus, plus to minus, plus to minus, their voltages are added up. Now I've got a simple circuit with 2 resistors in series here. These are 470 ohm resistors. Now if I look here, just get that so that's visible. There you go. Each of these resistors is consuming half of that voltage. So that's 1.9 there and 1.9 there. So what does that mean? Well, we look at this. We can work out how much current just by knowing the resistance and knowing the voltage drop across it. We know that 1.9 divided by 470 is 0.004 amps. So that is having 0.004 amps consumed across it. Now they're added in series, so those resistances added up and the voltages added up, meaning you're still going to get 4 milliamps across this whole system. 4 milliamps is basically flowing across here.
We'll look at this in Circuit Wizard. It's a nice way of demonstrating theory. So here I've got a similar series circuit. So they're sharing this 6 volts, 600 ohms each, 2 volts drop across each one. So you think of the resistance, think of a voltage to drop across each component as it consumes the power. 6 to 4 volts, 4 to 2 and 2 to 0 volts. So you're measuring voltage across something. It's often called potential difference because it's a difference between that bit and that bit. Whereas the current, you actually measure it through the wire. So if you're looking at the same circuit with voltmeters and ammeters, we're connecting the ammeter in line like that. Or here I've just got it, I can't fit it in line there, so I'm just cutting the circuit and actually sending it through the ammeter. Whereas the voltmeters are measuring across it. So you can see 4 volts across these two dropped, 2 volts dropped across here. And then these are both measuring 3.33 milliamps, which is 6 volts divided by 1800 ohms, the total resistance, if you think of I equals V over R. And here we've got this handy little thing. You can see the voltage levels here. You can see color coded, see as they drop, or even more useful is current flow, because it will show the color of the voltage and the speed at which things are flowing as well. So that's series when things are in line and they share the voltage. Now you might find, for example, if you're buying an LED, one of those power LEDs, let's say 3.6 volts, and you get a lithium ion battery that's 3.6 volts, you would plug them in series and you'd get 1.2 volts across each one, so they wouldn't be bright enough. You want to be able to plug them into parallel. Now I'll get on to something else in a minute with regards to LEDs specifically, but because they don't have their own resistance, really, they don't have much resistance, they actually consume more current than they should do if you just plug them in. So you do actually want to put a resistor in series with them. I'll demonstrate that in a minute anyway. Here in parallel, you can see the voltage is going highest amount in red here, right down to lowest amount. So 6 volts down to 0 volts across all 3 of these. I've only measured 1 across here. You can see that one is consuming 6 volts. Whereas the current is now shared. So they're all sharing this 30 milliamps to 10 milliamps. Now, what are these wires for? I was going to just show you what it would be like to measure across all of this. It's intentionally wrong because actually you're bypassing these resistors. The current's going to choose the easiest option, go straight through the ammeter, and it's going to have, if you imagine current equals volts divided by resistance. There's going to be hardly any resistance in here, so it's going to just consume too much current like that. So you want to be careful not to do this in a circuit. If I press play, you can see it's running 2.98 kiloamps, which is way too hot for something like that. Kiloamps is just something killer. It's not going to do anything any good. It's a lot of current there. So going back to my mention of having a resistor in series, here's a demonstration, little LED and a 300 ohm resistor burning away quite happily. I bypass that resistor and plug it straight across the battery terminals, and you can see it's not very happy now. It's consuming way too much power for its happiness, and it won't last long. Right, so that should hopefully get you a decent grounding knowledge of voltage, the pressure, current, the flow, and the power being the combination of two times together. So the total energy in watts. How resistors and resistance in ohms are going to reduce the amount of current flowing given a certain amount of voltage. And then if we add up resistances in series, we are going to share the individual voltage drop. So this is going to go 6 down to 4, 4 down to 2, and 2 down to 0 volts. Similarly, if these are individual cells, say they're 2 volt cells each, they're going to be added up to give a total power supply of a battery. In parallel, if you've got 2 volt cells connected in parallel, it's still only going to be 2 volts here. So this would be a combination of 6 volt cells, assuming they're all added up in parallel here. Whereas the load is all going to be using the same amount of voltage drop. So 6 down to 0 volts, but then the current's going to be shared. So it's going to be a third of the total current going through these. Hope that all makes sense. Join me in the next episode where we look at circuit diagrams and symbols and reading resistances.